I started using optical design and analysis programs when I started graduate school at the Optical Sciences Center in 1986. Since then, I've used ZEMAX, Oslo, Code 5, GLAD, and of course ProResearch's ASAP. Some of the applications as an engineer, I've designed spectrometers and imaging systems for large telescopes. I've worked on many different illumination designs, projection systems, a biohazard detection system, and the one I'm most proud of is an implantable optic for patients with age-related macular degeneration. My focus at BRO as Director of Training is to help enable other engineers to get that same feeling of satisfaction when they get to design their optical systems. Now I'd like to look at an imaging system analyzed using ASAP. We'll start by bringing in the optics to ASAP, and then we'll use SolidWorks to build the mechanical structures like the lens mounts, retaining rings, etc. We'll use ASAP to perform analysis as to where the light goes in the system, looking at stray light, scattered light, ghost images. We'll also take a look at the effects of obscurations. The general goal is to find out how the light makes it through the optical system. We can use the ASAP Path Explorer to do that. And by going through this analysis, we can make sure that the as-built system is going to meet the design specifications. Now we'll take a look at doing an analysis of an optical system in ASAP. In this particular case, what I've done is designed an optical system, in particular a Cook triplet, using a lens design program, although I could have also done the design and optimization within ASAP. I've exported that file from my lens design program and using one of the available translators have imported that into ASAP. So I now have the full lens structure within ASAP. I can then take that information from ASAP and export it as an IGES file, which I can then bring into a CAD program. The reason for doing this is so I can develop, or have my mechanical engineer develop, the mechanical structures necessary to mount this optical system. And let's take a look at doing that. And let's start by opening up a CAD program, and in particular, we're going to use SolidWorks. And what I'm going to do is open up my IGES file. And in the IGES file, I simply have the three lens elements. Here are the lens elements within SolidWorks. And we can scroll around to look and see that indeed we have our three solid objects that are the three lenses of this system. Let's take a more complete view at the system. And for now, we're going to concentrate on the right view so we can build up the mounting structures around each lens. So let's just look at the right view and let's change the format so we can actually see the structure. And at this point, what I'd do, or my mechanical engineer would do, is come in and build any necessary lens mounts, retaining rings that are necessary, possibly apertures, to use this system as designed in the original design program. We've already done that separately, so rather than going through the building of the geometry, let me close this file, and no, I don't need to save any changes, and let's open up the SolidWorks file that we've already created. Okay, so here's the file in SolidWorks, and again, let's expand this view to get a better idea of what's happening. And what we have are our mounts, our retaining rings around our lenses. We also have our lenses. Now, as a general rule, you don't want to export these optical components from the CAD program as an IGES or a CAD format file, because your lens design program and the ASAP translation understands optical surfaces generally better than the CAD programs do, so there's going to be less approximation if you use the files directly from the lens program. I only needed these lenses so that I could build the mechanical structure. Now that I have them, what I want to do is to delete those lenses. So I can come down and select each of the lenses and then delete them. Now that I've completed the structure, let me save the file. So I'm going to do File, Save As, and from the Save As type drop-down list, I'm going to select the ASAP specific GTX file format. And I'm simply going to call this Cook Rings. and then just save the file. And yes, I can replace the previously existing file. So now I have the mechanical structure in a format ASAP can read. So let's go back into ASAP. Let's start by looking at our first file. And in this particular case, I've already imported my mechanical geometry as well as my lens geometry. They've been saved as separate ASAP script files that I will read in each turn. And in this particular case, what I'm doing is applying properties to each of the surfaces, in this case to our mechanical mounting rings. And here I've applied a coating of black paint, or B paint, which is simply a 5% reflective surface. I can then modify this depending upon the type of analysis I'm trying to perform. So let's start by running the file. And the first thing we want to do is read in that geometry and verify that it indeed makes sense. And now ASAP will draw out the geometry of both the mechanical rings as well as our lenses. This will allow us to make sure that the position of each of the components is proper. And we now have our geometry, and we can use either the 3D viewer or the plot to verify the position of each of the components, and they appear to be in the proper orientation and proper location. So the next thing we'll want to do is to perform some analysis. And the first thing I'd want to do is define my sources and then propagate some rays through the system. And I have that in the file as well. And since I terminated my file or stopped execution here, I'm just going to issue a $IO command to ASAP and tell it to continue through the rest of this file. Now there are a couple of things we can do. The first is to look at our detector surface here, and we can see that indeed it appears that each of our sources are being properly imaged on this detector surface. But I also want to scroll in a little bit on this design, and I want to concentrate on this area right here. You'll notice that these two rays, one from the blue edge of field point and one from the red medial field point, actually intercept the mechanical retaining ring. They don't propagate all the way through our optical system. Now there are two reasons for this to be happening. The first could be that the mechanical mounts were manufactured or designed incorrectly and are actually blocking some of the light we want to propagate through our optical system. Or it could be that the optical designer used the technique of vignetting to deliberately clip out some of the energy in order to increase the performance across the system as a whole. In this particular case, this is the appropriate behavior, so I'm not concerned. This is one of the key things that you can do within ASAP, is you can verify that the real-world system will perform as the optical design assumed. Now, the next thing we want to do is perform further analysis. From a visual observation, it looks like our lenses are in the appropriate position, but ASAP can also perform any number of optical analysis calculations. We can look at items such as spot diagrams on detector surfaces. We can look at Rayfan plots. We can get information about the aberrations within the system. We can also perform point spread functions or MTF calculations. Next thing we're going to perform is to look at a point spread function and an MTF calculations performed within ASAP. We can then take this information and compare it to the data from the original optical design program to make sure that indeed the translation was proper, the mechanical structures aren't significantly impeding the performance, that the optical materials are properly defined, as well as the optical components. I'm going to run this file and we'll take a look at the output. We're going to do our analysis for an on-axis field point, so we're propagating a 21 by 21 set of beams through our optical system, and we're looking at both the point spread function as well as the MTF information. And here's the point spread function data, and here's the MTF information. And what we can see with the MTF plot and let's take a look at the three-dimensional plot, is the fact that this optical system designed to operate over a 30-degree field of view is not anywhere near diffraction limited, and we're seeing the effects of the aberrations in this optical system. And again, we can compare this to the lens design program itself and make sure that indeed the performance as defined by the ASAP system matches that created in the lens design code. One of the capabilities of ASAP that's very important in analyzing optical systems is the ability to analyze what really happens to the light. When light propagates through the optical system with a series of refractive components, all of the light doesn't transmit through. You're going to have Fresnel reflections from optical surfaces. You might have stray light, scattered light from surfaces. You could have interaction of the light with the mechanical components that will also create scattered ghosting type images as well. Within ASAP, we can ask for a simulation to include any or all of these particular effects. In this case, what we're just going to look at is the effects of Fresnel reflections from uncoated optical surfaces. We do that within our lens file, indicating our surfaces have a coating of Bayer. When we have the Bayer coating applied on surfaces, what ASAP will do internally is determine the angle of incidence of a ray upon each surface, and then based on that information, determine how much energy would be either transmitted or reflected. So let's take a look at the system. And in particular, we're only going to look at the on-axis field point simply because the ray paths will generate so rapidly, it's going to get very, very cluttered if we tried to look at more than one field point at a time. And here's the results of the calculation. We can see our direct ray path is coming in and forming its image at our detector surface. And we see a large number of these Fresnel reflections are also landing on the detector surface. One advantage is that in order for one of these rays to make it to the detector, they would have had to have reflected twice off surfaces. So they're all going to be very low intensity as a general rule, but depending upon the nature of the source in the system, they may or may not cause a problem in your final analysis. The other thing we want to take a look at is to zoom in a little bit, and what we'll notice is we see some Fresnel reflections off the front surface of the second lens appear to be forming an image inside the front optic. What we might want to do is take a look at that a little bit closer and to see whether or not that can adversely impact our optical system. And we have other capabilities, analytical capabilities in ASAP that will allow us to do more complete analysis on these individual ray paths. An important tool in ASAP to help you perform analysis on your optical system is what we call the Path Explorer. Path Explorer will search through a previously saved set of ray trace information and allow you to analyze that data. So what I'm going to do is run my file. And the Path Explorer can be accessed within the graphical environment by clicking on the Path Explorer Query Builder button on the button bar, or the information can be entered directly into your ASAP script file. In this particular case, let's take a look at the Query Builder option, and this will allow us to see some of the powerful features of this tool. We're going to start by looking at a system where we've traced the on-axis rays and also the Fresnel reflections off those surfaces. By selecting the Query Builder button, I'm going to open up my Query Builder dialog, and the first thing we do is notice in our data output window that there are a total of 216 paths within our system. All of these paths are now available for us to perform post-processing analysis on, and we do that by issuing any number of queries. What queries allow us to do are isolate particular subsets of those 216 rays. For instance, I can go through and look for those rays that divide at a particular surface or object within ASAP. Similarly, I can look for rays that end on particular objects, or rays that escape the system. These would be rays that did not end on an absorbing surface. I can sort the rays by their generation. The 0th generation are the first rays that come from the original source, and then each level of splitting and/or scattering will create a subsequent generation. I can sort on the number of times surfaces have been hit by rays, and many other capabilities as well. For example, in the case of this particular design, let's assume what we want to do is look at a little bit about the rays that might be forming an image inside this lens. And these are Fresnel reflections off the front surface of the second lens. So there are a couple of things we can do, and we're going to go through the process of building up a query. For example, I might want to start by eliminating those rays that are in the direct ray path. Those rays are in generation 0. So if I do a query type of generation and select a comparison type of greater than 0, what I will do is isolate those rays that did not come directly from the source. I can choose to give this ray set a name, and the reason I would do that is so I could possibly combine them later as a logical query using the query combiner. I can also apply the query to all paths, all 216 paths, or to any previous subset of the paths. What we're going to do right now, since this is just to isolate the rays, it's not what I'm actually interested in, I'm simply going to choose to run the query, and you'll notice the number of ray paths is now reduced to 205. I had 11 rays incident, 216 minus 11 brings us down to our 205 rays. Now what I want to do are isolate out from those rays only the rays that split off the front surface of the second lens. The query type for this is divide, and I need to enter the object name. And I know the name of the front surface of the second lens is lens2.front. And again, by not selecting this box, I'm going to apply it to the ray paths that were previously found. So to this subset of ray paths. Again, since this is an intermediate result, I won't bother to look at the graphics. I'll simply run the query. Now we've reduced our ray set down to a total of 63 ray paths. This is going to include both first order ray splitting as well as second order ray splitting because I have allowed that in my ASAP script. So the next thing I want to do is eliminate any of the second order paths that actually reach the detector. And the way I'm going to do that is to select the query type of escapes. So this time I'm just going to look at those rays that escape from the system. In other words, the last object in the ASAP system they interact with is a non-absorbing surface. This time I do want to look at the results, so I'm going to choose to display the results in the 3D viewer. And again, I'm going to run the query, and it turns out that there are only 17 ray paths remaining. Since we're done with our query, let me close the Query Builder dialog, which will end my Path Explorer session, and now I can look at the output in my window. What I'm seeing now are all of the ray paths, as well as the ray paths I'm looking at in particular. Let me change the background color. It will make it a little bit easier. I'm not interested in the original ray set, so let me choose to hide those. And I'm also going to make all of my optical components into a wireframe so I can better look through those systems. And I'm also going to hide my lens mounts so I get a better look at the lenses. And what we can see here is that indeed within this lens, these Fresnel reflections are forming an image. Now, if I'm using this optical system as a photographic objective and I'm taking pictures of scenery, this is probably not an issue. But if I'm using this to image a high-power laser, for example, even though the amount of energy in the Fresnel reflections is minimal, if this is a high-power source, I could be concentrating enough energy to cause thermal issues, either heating or even fracturing of this component. This is something that an ASAP analysis will allow me to see before the system is actually manufactured, and now, if necessary, I can go in and modify my design to eliminate this shortcoming. Additionally, if this optical system is being used as part of a relay system, and if I have another set of imaging optics over here. This could serve as a source into this system, and this image will actually show up on my final detector plane. And obviously, in most instances, that also will be unacceptable. So what we can do with an ASAP is now analyze all possible ray paths and get an idea of where the system is performing appropriately, as well as any limitations in the performance of the system. We are not limited to simply looking at sequential ray paths. The Path Explorer in ASAP can be accessed using the graphical builder from the button bar, or you can also enter the data into your ASAP script file. We're going to look at how to enter Path Explorer commands within the scripting environment, but the first thing I need to do is run my file. And in this particular case, we're going to look at a much larger distribution of rays, in particular an 11 by 11 input bundle, and we're going to look at Fresnel reflections from each of the surfaces. And as you can see, with even a moderate number of rays, the number of rays generated gets so large so quickly, it's hard to really go in here and perform any analysis simply by looking at the rays. So what I might want to do again is to use my Path Explorer, but in this case, let's take a look at how we do it in terms of the scripting environment. In this particular case, what I want to do is look at all of the rays that make it to the detector, and also get an idea of where all of the rays that didn't make it to the detector, at what surface within my design they exited out of the system. This is an example of Path Explorer commands within ASAP. This first set of commands is for the previous example where we looked at the Fresnel reflections off the front surface of the second optical component. What we want to look at now is all of the rays that ended on the detector that were not of the original ray bundle. So I've eliminated the 0th generation, and we're going to look at the rays that otherwise end on the detector. But rather than looking at the rays, we're going to look at the spot information. Where are the rays on the surface? We could also look at some summary statistics as well. To run the file, I'm simply going to insert my cursor above the commands I want to execute, and then go up and select the option of running from cursor. And what we see here are the surfaces that rays were on just before they exited the system, as well as those rays that are on the detector. And initially this looks a little bit scary, but if I open the list of objects, let me hide all of the original ray paths. And I'm also going to hide the mechanical structure so it will allow us to see things a little bit more clearly. And now let me rotate and zoom a little bit. And what we see on these surfaces, these little dots, let me change the color, background color, make it a little easier. These are where some of the Fresnel reflections were then lost from the system. These were rays that didn't make it through. And then we can also look at the detector and get an idea of the spread of the energy across the detector. By using the summary command, we can also get information about the energy, the total flux on the detector. And when I know that I initialized my energy to have units of 1 watt, this tells me that there is a very small amount of that energy actually making it to the detector as these Fresnel reflections, and that they're highly dispersed across that detector surface. So to sum it all up, what we can do in ASAP is we can design optical systems, or we can import optical systems that were designed in other programs. We can build mechanical geometry, or we can import mechanical geometry from a CAD program. We can perform any number of imaging as well as non-imaging calculations to determine the performance of the optical system, the radiometric distribution within the optical system, allowing us to do a full, complete, and thorough analysis of any of our optical or illumination designs.